Okay, today I want to start this set of notes. We will not have time to finish the whole thing, but I will finish it tomorrow in class. And then this, I don't want to say the second half of class tomorrow. Let's just say the last 12 minutes of class tomorrow, probably. You'll have a little bit of time to ask any questions about the WebAssign that's already out there. But there's also a WebAssign that goes along with this one. And we will have half of this thing done by the end of the hour today. So you could even start this new WebAssign tonight. As I told you before, there's lots of WebAssigns with this unit because we're learning to do new things. So it's a good way to start to learn something, to refresh. But when all said and done, we have to then look at it from an AP perspective, which is not a WebAssign perspective. All right, today we are going to review a couple things that we learned last year. Sometimes things might have seemed hard in grade 11. Now all of a sudden you come back to it, it's like, oh my God, it's so easy. Now I get it. And but we're going to talk about torque and rotational equilibrium. We did talk about those things last year. Does anyone remember what the equation for torque is? Torque is a T. Anyone remember? It's actually even a Greek T called tau. What does tau stand for? What does tau stand for? It's green. Force times what? Force times L. Let's call it L right now. Force times L. Okay, so force times L. F times L. F times L. All right. So when you apply a torque on an object, you cause the object to rotate. So let me give you two examples. If I put my pen here, and I'm just going to make my pen kind of like a hinge, like this, and then I apply a force like this, I make my pen rotate. One of the examples that we talked about last year was we had the door. So the door, like a big long thing, but I could kind of draw it as a line like this. And there's a hinge over here. And I apply a force to the door and then make the door rotate. So a torque is just something that produces a rotation. But a torque is made up of a force. So torque depends on both the force and the distance to the pivot point. So that L is a distance. I kind of wish it was a D. That's what is a D. But this L has a physics vocab term. That L is called the torque arm or the lever arm. But it's really the distance to the pivot point. All right, pivot points can be real or imaginary. So we're going to start today by looking at real pivot points, and then we'll do a couple of examples of imaginary pivot points. So we already said our equation is going to be T equals F times L. So let's look at the units. Force is going to be in newtons, and the torque arm or the distance is going to be in meters. So torque is in Newton meters. I could also do this in English units. So instead of measuring the force in newtons, I could talk about force in pounds, like how many pounds I pushed on something. And I could measure the distance in feet. And so it looks like pounds feet, but we say it in English as foot pounds. We say foot pounds. So it can be in SI or imperial units. All right, the next thing is if something is going to rotate, it needs a direction. So torque is really a vector, which means it has a direction. And the directions are clockwise or counterclockwise. Those are the directions, clockwise or counterclockwise. But when we take into account more than one torque, then we have to know that clockwise torques are negative and counterclockwise torques are positive. Negative and positive. All right, I think this will come back to you fairly quickly. I have 3 calculators up here. No batteries, no batteries. My batteries are low. So I'm not number crunching today. So you got to do your own number crunching, okay? Okay, here goes. All right, my first example is a wrench. And now I have to draw the free body diagram. So a wrench, I'm going to draw it as a line. And I plan to like pull on the wrench at the screw. So this screw is the pivot point. That would be a real pivot point. Like when I pull on a wrench, I'm truly pivoting from that point. And I'm going to take my hand here and I'm going to pull down with a force of 120. So it's kind of like an FA. And the distance from the force to the pivot point is L. So this distance is L. And L is 20 centimeters, and we turn it into meters, 0.20 meters. And then I'm just going to number crunch. The torque would be F times L. So that's going to be 120 times 0.2. And that answer would be 24, I think. 24 Newton meters. All right. Did I produce a clockwise torque or a counterclockwise torque? So you talk to yourself, you hold your finger at the pivot point, and you say, well, if I pull down here, that would make it go this way. That would go clockwise, right? So 24 Newton meters clockwise. So that's totally fine. Or you could have done this. You could have said, oh, well, when I pull down with this F like this, that would have made it go, that would make it go clockwise. And clockwise things are negative. So I should put a negative in for the 120. If you put a negative in for the 120, you would have got an answer of negative 24 Newton meters. Are you with me? And then you don't have to say clockwise because the negative sign tells you that it's clockwise. So it's going to be probably safer.
Good morning, FACO staff and students. At this time, all students who use bus transportation, you are released. Leave out the normal exit. Students who drive, you are staying here with us until 11:25.
Oh, I wish I was on the bus, right? No. Okay, let's come back together because I'm videoing. All right, as we go further, I am going to always use the negatives because then I don't have to think as much. And when we have multiple things going on, like 2 hands in the picture, I think the negatives will help me. All right, the next example is we have, let's call it a crowbar, like this. And I'm going to, I guess it's a long wrench. And I have this one hand right here. This hand, oh, I'm doing this in English units now. This hand is pulling with 20 pounds. This hand is pulling with only 10 pounds. And I need to know the L. I need to know the distance from the pivot point to the first hand. That is 1 foot. So I'm just going to put the 1 here. That'll be like easier than making a bunch of brackets. And then I need to know the position of the second hand. That's 2 feet, so I'll just put a 2 here. All right, so now I'm going to have net torque. Net torque means that I have more than one torque happening at the same time. So it's going to be the FL of the first torque plus the FL of the second torque. And both of these hands are making it go clockwise. So I do clockwise, clockwise, and I say clockwise things are negative, clockwise things are negative. So I'm going to plug in the negatives. So negative 20. How far is this force from the pivot point? 1. Instead of saying plus, I'm just going to put minus 10. And he is 2 from the pivot point. Negative 20 plus negative 20 is negative 40 Newton meters. That is the net torque produced, or 40 Newton meters clockwise. Oh, you are right. You know, last hour I videoed and I made 5 mistakes. So I told them that I was going to re-video 4th hour so I could make no mistakes. There's one. Okay. All right. So this is going to be foot-pounds. Okay. The next example involves an angle. So I'm going to come back up here to my equation and clean this up a little bit. So the force that you put in this equation has to be perpendicular to the torque arm. That's like a little tidbit thing we need to do. All right, so because I put the little perpendicular symbol in there, now let's look at this problem. And let's use this color. All right, so I have, let's call this a crowbar. Looks like a crowbar. And it's going to pivot here at point O. So I'm going to make that a pivot point. And I have somebody pushing down at 8. So I'm going to draw the down the way it's supposed to go. By the way, notice that it is at a right angle. It is perpendicular. All of these have been perpendicular so far. So this is 8. And how far is he from the pivot point? 5. So I'm going to put a 5 here. All right, the second force is happening at an angle. I have to find the force. This is the phrase that I use. It's perpendicular at the point of application. This is the point of application right there. So I have to be at that point. I got to be at point 2, perpendicular to the point of application. I'm going to put a 2 here. This is the F that I need. F. But that's not what they told me. They told me that this person really is pulling like sideways like this. So I'm going to put in what that person's doing. That person's doing this. And I'm going to call that 12. And I'm basically trying to make a triangle. And sometimes people don't know how to make the triangle. I just want the top of the triangle to be parallel to my bar. So like I got to keep everything like parallel. So they told me that this angle down here was 30. That tells me that this angle is 60. So I just got to find that F. So we could go over here and use cosine. Cosine of 60 would be adjacent over the hypotenuse. Cosine of 60, is that 0.5? 0.5 times 12, 6. F is 6. F is 6.
Huh.
What's the huh?
I felt the complete different way.
Well, okay. That's okay. You kind of did over here.
Yeah.
All right.
And I use sine.
And that's okay. You can do that. You can totally do that. The only issue is you have to make sure that you draw the F at 2 so you get his pivot point correct. Okay. All right, so I have two forces. Do you notice that this one force is clockwise? He's clockwise. So he's going to be negative. And this force here, if I pull up, would be counterclockwise. So he's going to be positive. So I'm going to do T net is going to be made up of two torques, FL plus FL. I oftentimes do the positive one first. So that would be 6. And his point of application is 2. He is 2 away from the pivot point. This guy is negative, so I'm going to put a minus. 8 times, he is 5 away from the pivot point. 12 minus 40. 12 minus 40 is 28. 28. Negative 28 Newton meters. Or 28 Newton meters clockwise. All right, do you remember doing those last year? Kind of? Are they okay this year? Yeah. Okay. All right, the next thing we're going to review is the word equilibrium. Last year, and this is technically the green stuff on window 2 back there, if something is in equilibrium, it means that the sum of the forces equals 0. That means if you add up all the x stuff, the positive x stuff has to equal the negative x stuff, and the positive y stuff has to equal the negative y stuff, and the sum of the torques has to equal 0, which means the counterclockwise things have to equal the counterclockwise things. If both of those conditions is true, it is in equilibrium. But we're going to look at it backwards. We're going to say, like, but I want something to be in equilibrium. Like in real life, it is in equilibrium. If it is in equilibrium, then you know the sum of the forces is 0 and the sum of the torques must be equal to 0. All right, here's our first example. And I picked this example because we're going to do a lab activity on this one. So a meter stick rests on a fulcrum. So this is a meter stick. And it's going to pivot on this piece, whatever that is. So it's going to pivot right here. So I'm going to put the pivot right here. That's the pivot point. The pivot point would be at like the 50 centimeter mark. So I'm going to call that point 5. Uh-oh. Is it still alive? All right, so the fulcrum is at the 50 centimeter. A 50-gram mass hangs at position 60. So I'm going to put an arrow down, and this is going to be at 0.6. 50 grams. Another 50-gram mass hangs at 74. 0.74. All right, but I got to figure out what the F is. So this is 50 grams. So the first thing I'm going to do is change grams into kilograms. I'll move the decimal over 3.050 kilograms. And how do you go from kilograms to newtons? Times by 9.8. And I remember from last hour, I think they told me it's 0.49. Someone verify that? Yeah. All right. So this is going to be 0.49. And this arrow is going to be 0.49. And those are newtons. All right, the question, where should a third 50-gram mass be placed to produce rotational equilibrium? Obviously on the other side. 0.49. But I'm not really sure where he goes. So what if we did this? I'll just go go, like I don't know where to put it, so I'm going to call that L. All right, I know this is not really rotating, but we're going to pretend it is. If we pretended it is, then these two guys would make it go clockwise. So I'm going to go clockwise, you're negative, clockwise, you're negative. And this one, I'm holding the pivot point and pulling down. That makes it go counterclockwise, counterclockwise, so you're positive. So I have 3 arrows in my story. So I'm going to write down T net has to equal 0 because I want it to be in equilibrium. So I'm going to have 3 arrows, FL plus FL plus FL equals 0. I'll do the counterclockwise guy first. 0.49. L, I don't know how far he is from the pivot point, so I'm just going to call it L. That's actually what we're solving for. All right, so when I get to the next guy, minus 0.49. This is a mistake people make. People plug in 0.6, thinking he's at 0.6. He is at 0.6, but it has to be the distance to the pivot point. So we plug in a 0.1. 0.1. And minus the next guy. How far is he from the pivot point? 0.24. 0.24. L equals. L equals. I do not know what L equals. Someone figure out what L equals? .34? 3.4? 0.34? All right, if it's 0.34, that would be like at the 34 centimeter mark. That kind of makes sense. That makes sense. You don't like that?
Maybe at 16. Maybe at 16. See, this got far away from the.
Ah! 0.5 minus 0.34. I did just what I told you not to. There's mistake 2. All right, so is it 16.16? 0.16. He's at position 0.16. He is 0.34 from the pivot point. Okay. So I made more mistakes last hour than I knew. I need to get more sleep tonight. Okay, the next one. A 50 Newton plank hangs from 2 ropes. The plank problem. All right, so I'm going to draw my plank like this. Sometimes people forget that that board, that plank has weight. It's 50 newtons. You got to put the weight of the board in the middle. Because normally we would take the object and shrink it into a dot, and then all of the FW comes off the dot. So this is where the dot would go, in the middle. All right, it hangs from 2 ropes. Let's put the ropes in. These ropes are not on the end. A lot of times it's common for them to be on the ends. By the way, ropes hold something up. Do you remember table legs? I'm going to go off on a small tangent. What if I had a table? You would draw that as a bar, and those table legs hold the table up. So Even legs of a bridge, supports of a bridge point upward. All right. A 75 Newton drum of paint sits 1 meter from the left rope. 1 meter from the left rope is 75. 75 is longer than 50. So I'm going to put 75. A 675 painter stands 1 meter from the other rope. 675. Wow, that's going to off my paper. I'm not drawing it real long because I'll be out of space. I should have drawn the other one shorter. 675. All right. Calculate the tension in each of the ropes. If this was a symmetrical picture, each rope would have the same tension. But it's not a symmetrical picture. This rope's got to hold up the heavy painter guy. So I'm going to call this FT. FT, that's tension. And I'll call this FT1, I'll call this FT2, because they're going to be different. They're going to be different. All right, so in real life, this board is perfectly flat. In fact, this board is in equilibrium. And I don't have a pivot point like I had here. I don't even have a pivot point because I don't want it to pivot. So in order for us to solve the problem, we have to have a pivot point. So this is when we're going to use an imaginary pivot point. You can put imaginary pivot points wherever you want. But we have 2 unknowns. So I'm going to put the pivot point right there because when I do that, I get rid of an unknown. How do I know I'm going to get rid of an unknown? Because how would I find his torque? It would be FT1 times the torque arm. What's the distance from FT1 to the pivot point? 0. And then it falls out. So it makes him go away. And now I only have 1 unknown. All right, so if he's going to go away, I have 1, 2, 3, 4 things. So these 3 on the bottom go clockwise. They would make it pivot clockwise from my imaginary pivot point. So they're all going to be negative. From my imaginary pivot point, FT2 rope, I'm pulling up, goes clockwise, counterclockwise, so he becomes positive. I have 4 things. So I'm going to go FL plus FL plus FL equals 0 because they're in equilibrium. All right, I'm going to do the positive thing first. That is FT2. I don't know what that is. FT2. All right. How far is FT2 from the pivot point? Look at the picture. The pivot point is here. 4, right? 4. All right. I'm going to put a negative now because I'm going to now do the paint. The paint is 75. And how far is the paint from the pivot point? 1. Now I'm going to do the board. That's 50. How far is the board from the pivot point? So it says that this is rope to rope is 4. So the board is like right in the middle. 2? See I'm getting 2? I think it's 2. Minus the painter guy, 675. He is 1, 2, 3 equals 0. I remember this one from last hour. FT2 equals 550 newtons. 5 newtons. I'm going to add that to my picture. This is 550. Do you think FT1 is going to be bigger or smaller than 550? Smaller. I think smaller because like the heavy painter guys over here. Do you remember the secret of how to find FT1? You could repeat the whole problem and make this a pivot point. You could do that. It works. Or you could do this. The sum of the forces equals 0. That means the x things, the positive x, the negative things equal. There's no x things in this picture, but there are y things in the picture. The up things have to equal the down things. How many down forces do we have? 1, 2, 3. Add those up. Add those up. The up things have to equal the down things. T1 plus 550 has to equal all of those downs. 800. Is it 800? So FT1 must be equal to 250 newtons. You good with that? Good? All right, we're going to try to eke out at least one more thing. 2 things. We're going to do this, and we're going to do this first box. Okay, then we'll call it a day. Okay, all that was a review from last year so that we could move to our new topic of rotational dynamics. So the first thing that we did is we looked at window 1 over there, and I'm going to call that the kinematics equations. And now you know the new rotational kinematics equations. That's why they're orange on the first window, and that's why I made them orange on the purple windows, because they're like the same things. All right, so now I'm looking at window 2. The next equation we ran into last year was F equals ma. I'm going to write down F equals ma right here. F equals ma. And we learned that equation in the topic of dynamics. So now we are trying to move into rotational dynamics. So what is the equivalent equation for F equals ma? Well, I don't want to just talk about the forces, because forces cause a rotation in our unit. So I care about the torques, not so much the forces. And we already know that, I'm skipping the M for a minute, we already know that the acceleration becomes a fish, becomes alpha. And then we have mass. And we're going to learn this part, I don't know if it'll be tomorrow or Monday, but in this topic, we don't care about just M, we care about where the M is. Like, I don't care about just the mass of the merry-go-round. I care about the position of the mass of the merry. So that doesn't make a lot of sense today, but go with me. It's called rotational inertia. So really what I'm doing is I'm taking this new equation, which is right here, equation T equals I alpha. T equals I alpha. And last year, we also talked about F net equals ma. So I'm going to make this T net equals I alpha. We now have to spend, well, we already spent time finding acceleration. You know A tan equals R alpha. You know the acceleration equations for alpha. So I feel like we've done alpha justice. We now have to learn how to find T net. That's what we're working on here. And then the next set of notes, we focus on the I. And then we can kind of like put it all together. So it's going to take us a couple days to put it all together. All right, I'm going to skip the units for each variable right now, and we're going to do the first sample problem. All right, so this is the same thing, T net, the same thing we were doing over here, except this time our things are rotating. A student applies a force of 500 newtons to the outside edge of a 6-meter diameter merry-go-round. So this time, when I draw my free body diagram, it's going to be the merry-go-round not just a line. And I still need a pivot point, but the pivot point's always going to be the axis of rotation. And so I'm going to draw this right here so I make sure I do this right. The student applies a force of 500 newtons to the outside edge. I want this to be the 500. So I'm going to say F equals 500. Remember when you find torque, that the F had to be perpendicular to the torque arm. So this is perpendicular. That tells me that this here is the torque arm, except you might call that the radius. So instead of writing an L for distance, we're going to write an R for radius. And the radius of this is going to be 3 meters. So I can see right now that the net torque is 1,500 Newton meters. All right, but that's not the question. The question is calculate the angular acceleration of the ride. So I'm going to write down my new equation, which is T net equals I alpha. And I'm looking for alpha. So in order to get alpha, I'm going to have to find T net. I'm going to have to find I, and then I can find alpha. All right, how do I get T net? Well, it's an FR. So that's going to be 500 times 3. So FL now becomes FR. I is not the mass of the merry-go-round. I depends on the shape of the merry-go-round. The merry-go-round is a circle, but it's solid. And because it's solid, that would be like a disc. So I'm going to go like this. A disc is going to be solid. A hoop is hollow a hoop would look like a ring, just a ring. And it's hollow on the inside. So a merry-go-round is more like a disc than it's like a hoop. So the I equation is going to be 1/2 mr squared. So the mass does matter, but the radius also matters. So this is going to be a 1/2, and the mass is 150. The radius is 3 squared, and then I can number crunch, and I now can find alpha. So I'm really just trying to show you where we're going with all of this. I'm trying to see if we did that one last hour. Yes, they got 2.2. What do you think the units are going to be? What are the units for angular acceleration? Radians per second squared. Look at the second purple window. Look at the top equation. What color is it? Purple. What does purple mean? You got to use radians. That's what purple means. All right. Calculate the angular acceleration of the ride. I just did that. But look at the next question. Now, the student who's applying the 500 is going to jump on the ride. So when he jumps on the ride, he's right here. He jumps on. Calculate his tangential acceleration. He now feels pulling on his stomach. His hair's blowing in the wind. How can you calculate his tangential acceleration? Any ideas? Think yesterday? Oh, come on. Oh, come on. Say that again, Zena? No, you just said it right. It's what? A-tan? R-fish? A-tan equals R-fish? Good stuff. All right, 3 times 2.2, 6.6 meters per second squared. That's yesterday's stuff now. All of this stuff keeps adding on top of each other. That's the hard part about this unit. Everything adds, everything adds. If you start to fall behind, you are sinking in a well deeper and deeper and deeper. So get yourself out of the well tonight. FYI, you can now finish last night's WebAssign. And you know what? You know how to do a lot of things on the new WebAssign also. And we'll pick up and finish the notes tomorrow. Okay?